Hello and welcome back. In today's video, we are going to talk about the problem of the step potential. Now, this is a standard problem in quantum mechanics which has two different cases. One in which the particle has an energy greater than the step potential V0, and second in which the particle has an energy less than the step potential V0. Now, the second case I'm going to discuss in my next video where I'm going to solve its entire solutions completely. But in today's video, I want to look at the first case scenario. What happens when an otherwise free particle suddenly encounters a step potential where the energy of the particle is greater than the potential V0? Now, classically speaking, this kind of a problem is not very difficult to understand. As a free particle encounters a potential, it has a certain velocity, but suddenly its velocity will decrease as it keeps moving forward. However, in quantum mechanics, it is not necessary that the particle will keep moving forward. In quantum mechanics, there is a probability that the particle might get reflected back, and there is a probability that the particle may transmit through. Whether reflection will happen or whether transmission will happen is equally likely, and we can calculate the probabilities associated with them based on our theory. So therefore, the quantum mechanical problem is very interesting, that even though the approaching particle has energy greater than the step potential, there is a likelihood that the particle might get reflected back or might get transmitted through, and it is the quantum mechanical theory which will predict what is the probability of reflection and transmission. And this could be better understood by imagining the approaching particle not as a particle, but as a matter wave. Imagine a matter wave which is encountering a sudden jump in the potential. Then that matter wave has a certain likelihood of getting reflected back with lower amplitude, and some of it may get transmitted through. When you imagine it like that, then everything becomes clear, because in quantum mechanics, the motion of a particle is best approximated by the motion of some kind of a wave. Now, this is a very ideal scenario because usually we do not have this kind of a step potential in realistic situations. Usually the potential increases gradually depending upon the nature of the force. So for this kind of a potential to exist, there has to be a very sharp force that acts on the particle at x is equal to 0. We are again making this a very simplistic scenario because we want to solve the Schrodinger equation to get simple answers first before making it complicated. So therefore, we are taking this idealized example of a sudden jump in a potential to a constant value and a particle approaching that kind of a situation. So in this video, I'm going to solve the Schrodinger equation for this problem, find out the plane wave solutions, and then obtain the reflection and the transmission coefficient, which will give us the probability of reflection of the particle at x is equal to 0. Let's begin. If you are a student preparing for various examinations in India like Physics IIT JAM, NET or GATE Physics, then you can find extremely dedicated courses, both live and recorded courses, on our platform 𝓬𝓐𝑎𝑠𝑠.in. So here I have divided this entire scenario into two regions. Region number 1, in which the particle was initially free from -infinity to x is equal to 0, and region number 2, in which the particle encounters this potential which extends to positive infinity, which is beyond x is equal to 0. So what we want to do is we want to solve the Schrodinger equation, the time independent Schrodinger equation, in both region number 1 and region number 2. So in the region number 1, the Schrodinger equation, let's suppose, has a solution associated with its wave, and I call it psi1. Okay, so if I call it psi1, then minus h cross square upon 2m, you have d2 psi1 upon dx2 plus v psi is equal to e psi. All right. Now in region number 1, the potential is 0. Therefore, this equation simply becomes d2 psi1 upon dx2 plus 2me upon h cross square psi1 is equal to 0. So these are all psi1. Now here, if I imagine this constant to be k1, then this equation simply ends up becoming d2 psi1 upon dx2 plus k1 square psi1 is equal to 0. So I'm imagining this constant to be k1. All right. What is the standard solution for that? Okay. So standard solution for that, I'm just going to write it here because I'm going to save this left hand side for further calculations later on. Okay. So in region number 1, the solution for this kind of a standard differential equation is an oscillatory solution that can be written in this particular manner, where psi1 is equal to some constant a e to the power iota k1x plus another constant b e to the power minus iota k1x, where what is k1? k1 square is simply equal to 2m capital E upon h cross square, where h cross is Planck's constant upon 2 pi, m is the mass of the particle and E is the energy of the particle. Here we end up getting an oscillatory solution. I have written this in the most general form, which includes the complex part as well, instead of writing it as a sum of sines and cosines. Now if you look at both these two solutions, it's a linear sum of e to the power positive iota and e to the power negative iota. What do they mean? Essentially what is happening is, if you look at this kind of approaching particle, this approaching particle, as I just now mentioned a couple of moments back, can be imagined as an approaching wave. Okay, you can think of a matter wave which is approaching this barrier as it is coming from left to right, something that looks like this. Okay. Okay, this matter waves comes from left to right, approaches this barrier, and what happens is that something interesting happens. This matter wave, some portion of it goes back and some portion of it transmits through. So if we look at the backward moving matter wave, let me make it something like this. This is the backward moving matter wave, let's suppose. So in that sense, in this region number 1, two solutions exist. One is the forward moving matter wave, okay, the forward moving matter wave, and the other is the backward moving matter wave. Okay, this is what this is. The first part, this represents the forward moving incident wave, incident plane wave solution. Okay, this we can call as psi incident, INC. Okay, and the second part here, this refers to the backwards moving reflected wave, which I am going to call as psi reflected, REF. So when the wave approaches this barrier, it experiences some amount of reflection, and that reflected wave is psi REF, and the incident wave is psi INC. So when I solve the Schrodinger equation in region number 1, then the solution comprises of these two solutions. One is forward moving plane wave solution, another is backward moving plane wave solution. I hope the scenario is becoming clearer in your mind. So in the same fashion, we can also solve the Schrodinger equation in region number 2. What happens when this wave approaches this barrier at x is equal to 0? So it suddenly encounters this constant potential. So now, if we look at region number 2, we will get again the time independent Schrodinger equation, minus h cross square upon 2m d2 psi, let me call it psi 2, okay. Psi 2 essentially is the solution of the Schrodinger equation in region number 2. So this becomes d2 psi 2 upon dx2 plus v psi 2 is equal to e psi 2. So what is v in region number 2? It is v naught. So therefore this simply ends up becoming d2 psi 2 upon dx2. So this goes to the left hand side, so e minus v naught, and then comes back, so plus 2m upon h cross square e minus v naught psi2 is equal to 0. Again, this is a standard differential equation that looks somewhat like this, except the constant here is different, and let me call that constant is equal to k2 square. So this is d2 psi2 upon dx2 plus k2 square psi2 is equal to 0. So similar fashion, this kind of a differential equation leads to an oscillatory solution in region number 2. So let's look at region number 2 now. So if we look at region number 2, what is the nature of the solution? So psi2 is equal to, let's suppose, some constant c e to the power iota k2x plus d e to the power minus iota k2x. Now the Schrodinger equation is giving us a similar kind of a solution in region number 2. However, we have to keep in mind that not always we have to accept the nature of the Schrodinger equation solutions, because the Schrodinger equation solutions, being a solution of the Schrodinger equation itself is not enough. We have to make comparisons with the actual system and see whether or not we accept some of these solutions and reject others. Alright, based on whether the solutions make sense. So just like in the region number 1, you had an incident wave approaching from left to right, and then you have a reflected wave approaching from right to left. Here also we get a wave going from left to right and another wave going from right to left. Now this solution is not really possible. Why? Because this constant potential approaches to infinity. Okay, this constant potential starts at x is equal to 0 and extends up to infinity. Now if you imagine a wave approaching this kind of a sudden jump in potential, then you can understand that the wave will get reflected back. But if for all positive x-axis there is no change in the potential, if the potential itself is constant to infinity, then there is no possibility of reflection. You see, some of the wave will get transmitted through, but they will never get reflected because there is no jump in the potential in the positive x-axis. Are you understanding what I'm saying? So because this potential is constant, the transmitted wave will go forward, but it will never get reflected back because there is no potential barrier ahead of it. So therefore, the only way we can rationalize this is we can say that d is equal to 0. That's all. Okay, because d is equal to 0 because there is no reflection in the positive x-axis. There is no potential jump or potential barrier in the positive x-axis. All right. So d is therefore equal to 0. However, what does this term mean? This itself is still possible. This is the forward moving transmitted wave. Okay, it is a transmitted wave which I am going to call as psi TRAN, transmitted wave, where K2 is basically equal to K2 square is basically equal to 2m upon h cross square E minus V naught. Okay, I am keeping these terms here because I am going to do a lengthy derivation. I want to refer to these terms in the left hand side. So particle approaches from left to right. You can imagine the particle to be a matter wave. This is the incident wave. It experiences reflection. This is a reflected wave. It experiences transmission. This is the transmitted wave. Reflected wave in region number 2 is not possible. So we have taken capital D is equal to 0. Now the question is, I want to figure out what is the probability of reflection and what is the probability of transmission. We can do that by applying the various boundary conditions to these plane wave solutions that we have obtained. Alright, let us apply the boundary conditions here and then proceed with the calculations. So what are boundary conditions? You see, whenever a particle in quantum mechanics encounters changes in the potential, then we have to include boundary conditions, which essentially mean that we are interested in a continuity of the solution as well as a continuity of the derivatives of the solution. This is because we want the probability density of the particle to vary in a continuous manner, and we also want the linear momentum of the particle to vary in a continuous manner. Therefore, boundary conditions are important. Otherwise, there are going to be sudden jumps in the probability density and linear momentum. We don't want that, which means that we are interested at x is equal to 0. So whatever the nature of the solution here and solution here, at x is equal to 0 must be continuous and its derivatives must be continuous, right? So that means if we take psi 1 at x is equal to 0 and if we take psi 2 at x is equal to 0, they must be continuous. There cannot be a discontinuity at x is equal to 0 because discontinuities are not allowed for acceptable wave function solutions. So if I do this, then let us apply this here. So if x is equal to 0, psi 1x becomes capital A e to the power 0 plus capital B e to the power minus 0, which is again 0. And if we look at psi 2, then I have capital C e to the power 0. This simply means that A plus B is equal to C. Now, this was the first boundary condition. Let us apply the second boundary condition for the derivatives, okay? So, which says that if I take the derivative of psi 1, d psi 1 upon dx at x is equal to 0, and if I take the derivative of psi 2, d psi 2 upon dx at x is equal to 0, then they should both be equal. That's what it means. The continuity of the derivative of the plane wave solution. So for that, the derivative of psi 1 comes out to be iota k1 a e to the power iota. So e to the power, essentially it will become 0. So it will become e to the power 0. And then we have minus iota k1 b and then again e to the power 0. Left hand side, right? What about the right hand side? The right hand side simply ends up becoming iota k2c e to the power 0. So this simply means that iota k1 a minus b is equal to iota k2 c. All right, iota gets cancelled and we are left with a minus b is equal to k2 upon k1 c. Now here what we can do is, let us imagine that this is point number 1. Let us imagine this is point number 2. And let me add point number 1 and point number 2. So if I add 1 and 2, what do I get? I get a plus b plus a minus b, which is equal to, so here I have, oh, this should not have been 0, I'm sorry. Okay, this should have been c, okay, e to the power 0 is 1, so this should have been c, okay. So this becomes c1 plus k2 upon k1, that's it. So this becomes, b gets cancelled, 2a is equal to c k1 plus k2 upon k1, and finally we have c upon a is equal to 2k1 upon k1 plus k2. That's it. Let's say that this is point number 3. This is going to be important for us later on. So I'm going to write it in the left hand side just to keep it for our calculations later on. We have obtained that c upon a is equal to 2k1 upon k1 plus k2. This is what we have obtained, one of the expressions. Now if I substitute this in point number 1, okay, c and c is equal to essentially 2k1 upon k1 plus k2a. So therefore b becomes this minus 1, so 2k1 upon k1 plus k2 minus 1a. So this ends up becoming b upon a is equal to 2k1 minus k1 minus k2 is k1 minus k2, and in the denominator you have k1 plus k2. That's it. Let's suppose this is point number 4, and let me write it down here again just for later purposes, that b upon a is equal to k1 minus k2 upon k1 plus k2. And now that we have obtained the values of these constant a, b and c, now it is going to be straightforward. I want to calculate the probability of reflection of the wave and the probability of the transmission of the wave. All right. So let's proceed to that part of the calculations. So to calculate probabilities of reflection and transmission is not difficult. We just have to invoke the concept of probability current density. You might remember in one of my earlier lectures I talked about probability current density. So whenever a quantum mechanical particle is in motion, in the theoretical framework we are not really aware of the particle itself. We are only aware of its wave function solution, and the wave function solution is associated with a probability density. So if a particle's motion is to be replicated theoretically, we are only essentially replicating the flow of the probability fluid, right? So if a particle is moving forward, the probability associated with it is also moving forward in the manner of a fluid. Particle moving backward, the probability also in the manner of a fluid is moving backward. So the current associated with that fluid motion is called probability current density. I've discussed it in detail in one of my previous lectures. We can use that concept here for the plane wave solution. So these are plane wave solutions which have a purpose. Okay, you must be familiar with the fact that usually for free particles we don't use plane wave concept, we use the concept of a wave packet. But here, because we are interested in calculating reflection and transmission coefficients, then this plane wave solution is sufficient, because that will give us an idea about the probability current density and the corresponding reflection and transmission coefficients. So if we want to figure out what is the reflection coefficient, the reflection coefficient is essentially the probability current density that is associated with the reflected wave upon the probability current density associated with the incident wave. So essentially it is reflected current density upon incident current density. So if we can calculate the current, so if I know the current density associated with the reflected wave upon the current density associated with the incident wave, that will give us the reflection probability. Similarly, for the transmission probability T, I need to know the transmitted wave current density. So transmitted wave current density upon incident wave current density. So this is equal to J transmitted upon J incident ratio. Alright, so if you know how to calculate the current density of any kind of a plane wave solution, then it is easy to figure out the reflection and the transmission coefficients. So let's do that. You must know that the current density expression or probability current density expression is what is given by J is equal to iota h cross upon 2m psi star. For 1D functions we have d psi upon dx minus psi d psi star upon dx. So here I'm interested in calculating the probability current density for all the different kinds of waves, the incident wave, the reflected wave, and a transmitted wave. So let me write down everything one by one. So what is the incident wave? Psi incident, what is it? It is this, A e to the power iota k1x. What is the complex conjugate of the incident wave? It is A e to the power minus iota k1x. Alright, similarly, so let me now rub some portion of the board to make space for the further calculations. If you want, you can pause the video here and complete your notes if you're making notes with this video. Pause it here, complete your notes. Let me move forward with the further calculations. So what is the current density for the incident wave? Let's calculate one by one, J, I and C. Okay. So current density for the incident wave is, I made a mistake, this should have been here. This should have been here. Okay. The current density is iota h cross upon 2m, and then within brackets psi star d psi upon dx minus psi d psi star upon dx. So for the incident wave, we have psi star. I'm just going to plug it in, okay. The formula is essentially for incident wave, psi star incident, d upon dx psi incident minus psi incident, d upon dx psi star incident, right? But I'm just going to straightforward plug it here for faster calculation. So psi star, so this comes out to be essentially equal to iota h cross upon 2m. So psi star incident is equal to A e to the power minus iota k1x, and then you have d upon dx of psi. So this is iota k1a e to the power iota k1x, and then minus you have psi, which is A e to the power iota k1x, and then d upon dx of this, so it becomes minus minus plus iota k1a e to the power minus iota k1x. Not very complicated, just these terms gets cancelled, alright, and then you are left with iota h cross upon 2m, and then here you have iota k1, you take it out, so iota k1 you take it out, and then you end up getting twice a. So 2 gets cancelled again, all right, and iota becomes iota square, which is minus. So this is equal to minus, and then this should be a mod square. Sorry, I'm making some silly mistakes. Just a moment. Okay. Let's clear my head. All right, just a moment. Sometimes it happens. So whenever I'm doing lengthy calculations, here or there a silly mistake always ends up happening. What can you do? I can only correct it at a later stage. So when I took the complex conjugate, right, then I do not yet know the nature of these constants, right? So therefore, I should also take complex conjugate of these constants, okay, to be precise. If they are real, fine. If they're not real, just for the sake of being accurate, I must take complex conjugate of these constants. So therefore, the complex conjugate of this should be a star, and the complex conjugate of this should be a star here. So this should be, to be precise, 2a mod square, okay, a mod square. So the 2 gets cancelled, and then you have a mod square. Okay, so finally the current density comes out to be minus a mod square h cut k1 upon m. This is the current density for the incident wave. It seems I made one more mistake. Actually, there should be a negative sign here. Okay. In the definition of the current density, a negative sign here, which makes changes to my calculations. There should be a negative sign here, here, and finally it should become positive. All right. Yeah. Now, once you can calculate the current density for the incident wave, you can easily do that for the reflected and the transmitted waves. They have a similar form because the solutions have a similar look to it. But I'm going to do it for the sake of completeness. If you want, you can skip ahead because you can easily see from here that how the current densities for the reflected wave and the transmitted wave would look like. Okay, again, minus iota h cross upon 2m. So for the reflected wave, I have psi star first. So b star and then e to the power iota k1x, and then I have d psi upon dx. So this becomes minus iota k1 b e to the power minus iota k1x minus, and here I have psi for b. So this is b e to the power minus iota k1x, and then these d upon dx of this, which is iota k1 b star e to the power iota k1x. So clearly you can see that these terms gets cancelled, and what you are left with is minus iota h cross upon 2m, and then here you have iota k1 I can take out, and you're left with 2 b mod square. So 2 and 2 again gets cancelled, and minus and the iota square gets cancelled. So you're left with, so here again there's a minus minus sign here, so this minus minus will become plus. So therefore iota square will essentially become minus b mod square h cut k1 upon m, similar to the previous result. And finally, if we want to find a current density for the transmitted wave, this comes out to be minus h cross upon 2m. So for transmitted wave, I need psi star. So this comes out to be c star e to the power minus iota k2x, and d by dx of this is iota k2c e to the power iota k2x minus, and then psi you have c e to the power iota k2x, and d star, d upon dx is psi star. So this is minus minus plus, you end up getting iota k2 c star e to the power minus iota k2x. I hope you are able to decipher what I am writing. Okay. Anyways, if you understand the calculations, they are very simple and straightforward. So this ends up essentially becoming minus iota h cross upon 2m, and then here you have iota k2 I take as common, and 2 c mod square is left. So this becomes finally iota square and minus gets cancelled, c mod square h cut k2 upon m. So these are the probability current densities. Once you have figured this out, now we already know the ratios of C upon A and B upon A. I can plug them in to get the final answers of the reflection and the transmission coefficient. So let's do that. The reflection probability or reflection coefficient. That is equal to J, which is the current density for reflection, upon current density for incident wave mod. Now what is J reflection? It is this minus B mod square h cross k1 upon m. J incident, so 1 upon A mod square h cross k1 upon m whole mod here. okay, because this is a constant, this is a positive number. So this gets cancelled and you are essentially left with B upon A mod square. That's it. What is B upon A? It is this K1 minus K2 upon K1 plus K2. So this becomes K1 minus K2 upon K1 plus K2 mod whole square. So this can be written as, if I take K1 common and out, it becomes 1 minus K2 upon K1 divided by 1 plus K2 upon K1 whole square. But what is K2 upon K1? If you look here, K2 upon K1, K2 square upon K1 square. So root over, this is basically equal to, this is root over 2m upon h cross square, and 2 upon h cross square gets cancelled. E minus V naught upon E. So this is 1 minus V naught upon E. This is K2 upon K1. So if I substitute this here, this simply ends up becoming 1 minus root over 1 minus V naught upon E divided by 1 plus root over 1 minus V naught upon E whole square. So if I take, if I write this as E minus V naught, okay, E minus V naught, take the E out, I can write the answer here. In fact, R is equal to, the most simplest expression should look something like this, root E minus root E minus V naught upon root E plus root E minus V naught. That's it. This is the probability of reflection of the particle at x is equal to 0. That's it. Similar fashion, we can also calculate the transmission probability. Transmission probability we have T is equal to current density for the transmitted wave upon current density for the incident wave, which comes out to be, for the transmitted wave it is C mod square h cross k upon m, and for the incident wave it is 1 upon a mod square h cross k upon m mod. Here these terms gets cancelled and I am only left with C upon a mod square, which is nothing but this that we have obtained beforehand, 2k1 upon k1 plus 2. This should not get, the k should not get cancelled, because the k is supposed to be, this is supposed to be k2 and this is supposed to be k1. So only h cross upon m gets cancelled. So this should actually be k2 upon k1 C1 upon a mod square, which is nothing but this. So if I substitute this here, I end up getting k2 upon k1, and we end up having 2k1 upon k1 plus k2 whole square. All right, we can simplify this further. How? By putting this k2 upon k1 is equal to this. So this comes out to be equal to 2 square is 4. K2 upon K1 is root over 1 minus V naught upon E. Again, if I take K1 common, it will get cancelled. So I should be left with 1 upon root over 1 plus K2 upon K1. So 1 plus root over 1 minus V naught upon E in this manner. So if I simplify this, there should be a square here. If I simplify this, this should give us 4, and here I will get E minus V naught upon E, and here I would get 1 plus root over E minus V naught upon E1 whole square. This finally simplifies to T is equal to 4 root over E minus V naught upon root E plus root E minus V naught whole square. That's it. So therefore, we have now obtained the transmission probability as well as the reflection probability of our particle which is interacting with a step potential. So if you look at the transmission probability in terms of E upon V naught, so when the particle's energy is very much comparable to the potential, then the transmission probability is very low. But as the particle's energy increases, the transmission probability also increases. So we can plot the reflection probability and the transmission probability in a graph and make a very simple comparison and look at an analysis of the different kinds of situations possible. So if you are making notes, please take a snapshot or pause the video here and complete your notes. Let me rub and proceed forward with the final conclusions of today's lecture. So if we plot the reflection probability and the transmission probability in this kind of a graph, where the x-axis is E upon V naught, so it's the ratio of the energy of the particle to the potential barrier V naught, then you can clearly see that when E is equal to V naught, so this is 1 by the way, okay, it starts with 1. So when E is equal to V naught, then the reflection probability is maximum, transmission probability is 0. As the particle's energy increases, then the reflection probability decreases and the transmission probability increases. So you can clearly see that this is very much in contrast to a classical scenario, because in a classical scenario, a particle approaching a barrier where the particle's energy is greater than the barrier would always transmit through. But in quantum mechanics, that doesn't always happen. It has a probability of reflection and transmission. So when the energy is comparable to the barrier height, it has a greater probability of reflection. When the energy increases, the reflection probability decreases and the transmission probability increases further. You can think of this scenario by replicating this kind of a system with a large number of particles. So if you bombard this kind of a potential with a large number of incident electrons, then some of these electrons will proceed forward, some of the electrons will proceed backward. This is the analysis that comes when we look at reflection and transmission using matter waves. So an incident wave comes, a portion of it is transmitted through, portion of it is reflected back. You can see that the wavelengths are different because the wavelength has to do with the wave number K1 and K2. Here K1 is greater, here K2 is less than K1, so it has a greater wavelength or lesser wave number. So we can note a couple of things here. So point number 1, the sum of the reflection and the transmission coefficient would always be equal to 1, because at the end of the day, it's a matter of probability. It either moves forward or it is reflected back. Probabilities always add up to equal to 1. Second point to note is when the energy of the particle is approximately equal to V naught, then reflection probability is equal to 1, particle will most likely be reflected back, and transmission probability is approximately equal to 0, as you can see from this graph here. And the third case scenario is when the energy of the particle is very, very large compared to V naught. When the energy of the particle is very, very large compared to V naught, reflection probability is approximately equal to 0 and transmission probability is approximately equal to 1. That means if the particle has a great energy compared to the potential, then the potential is unable to affect the motion of the particle. The particle will most definitely transmit through. So this is the standard problem of a step potential where a particle encounters a constant sudden potential at x is equal to 0. When E is greater than V naught, we end up getting a situation where the particle has a likelihood of either getting reflected back or transmitted through. Now, the second case scenario in which E is less than V0, that is also interesting scenario. In that scenario, in the next class, we will see that even though the particle has an energy less than V0, it has a probability of tunneling through. Quantum mechanics, you see, allows for tunneling. And we will see that interesting feature in the next video. This is all for today. Thank you so much. This is all for today. Take care. Bye-bye.